Alcohols. So the next chapter we're going to talk about is on alcohols. So remember, an alcohol has a carbon-oxygen-hydrogen bond, and we can classify alcohols in 3 different ways. So there's a number of different ways we could do this. If we've got this. And R. If the carbon which the OH group is bonded to is got one R group, we would call this a primary alcohol. Primary, secondary, or tertiary. So that's just one general classification of alcohols. There's a slight pKa difference between the two of them. Sorry, between the 3 of them. Typically, tertiary alcohols, they are harder to remove the proton for. So once they've been removed, they're slightly more basic. And we saw that with when we're using the tert butoxide as a base in organic 2. So that's one way to classify alcohols. Now, we just went through a whole bunch of different reactions that we've used to prepare them. So some other characteristics of alcohols is that they can be Lewis acids or Lewis bases, depending upon what they're reacting with. So the example we just did one example was when it was reacting with BF3. In that instance, it would be behaving as a Lewis base. But if it's reacting with sodium hydride, in that instance, it would be behaving as a Lewis acid. So it can behave one way or the other. So ways to make synthesis. The whole section from alkenes you could have the anti-Markovnikov or the Markovnikov addition of water across a alkene. So hydroboration gave the anti, oxymercuration gave the Markovnikov. So those were 2 different ways of making alcohols from alkenes. Let me think. And we've seen some things before. Let's see. The SN1, SN2, E1, E2 section last term. You will remember that if you had an alcohol and you reacted it with, say, HBr. If it was a tertiary alcohol, you could do basically an SN1 reaction where you'd make a carbocation intermediate. Let's just leave it like this. We need our Br minus bromide. So we could do something like this for a tertiary alcohol. If we did something for a primary alcohol, the mechanism would have to be slightly different. It would be along these lines. Where it would have to be an SN2 reaction. In fact, you did this one in the lab. No. You did the other one in the lab. Okay, so. But this would be an SN2 reaction. The key point is that the alcohol gets protonated by the acid to become a good leaving group, and then we can do the substitution reaction. So in both of these cases, we've got water as the leaving group. Now, these reactions, they work. Problem is, though, is that there's a lot of functional groups that are acid sensitive. So if you had a really complex molecule, this type of chemistry isn't going to work because the acid's going to react with something else. But both of these things are possible. The other thing that we did, which you might remember, is that you could convert an alcohol to a good leaving group. And the reagents we used for that were something which looks like this. I'll just put an R group here because there's a variety of different R groups that are possible. And we use pyridine, dichloromethane, and now we have our leaving group. And you remember that we had abbreviations for these depending upon what the R group was. It could be the OMS, the OTOS, the OTF, the mesylate, the tosylate, or the triflate, depending upon what R group was. And so all of these are excellent leaving groups. And so you could start with an alcohol which isn't a leaving group and convert it to something that was a leaving group. So that was something we did at the end of Organic 1 for the SN2 reaction. So you can convert alcohols into sulfonic ester sulfonates, and all of these are really excellent leaving groups. Right, so what we're going to do today is talk about some of the new chemistry that we haven't seen before. I guess the biggest interesting thing is that if you've got an alcohol, there is a sort of a relationship with carbonyl compounds. So in so let's call this alcohol. So in alcohol, we basically got a carbon-oxygen sigma bond. And for the carbonyl, you got a carbon-oxygen sigma bond and a carbon-oxygen pi bond. And so all we need to do to go from one, there's sort of this relationship where conceivably you should be able to convert one to the other and vice versa. So anytime you're adding, chemists have got a, one second. My apologies, don't leave a cat in the room with you, or they go crazy. So there's a relationship, well, organic chemistry, chemists, like organic chemists are, what's the correct term here? Simplistic in the way that they view certain things, particularly this relationship from going from an alcohol to a carbonyl and vice versa. So in one case, you'll notice that there are hydrogens on the carbon and the oxygen, i.e. in the alcohol case. In the carbonyl case, they're gone. So anytime you're removing hydrogen and adding oxygen to a carbon, we call this process an oxidation. And anytime you're removing a carbon-oxygen bond and adding a carbon-hydrogen bond, we call this process basically reduction. If you talk to a physical chemist or inorganic chemist, oxidations and reductions are talking about electrons. It's true, we could do an electron, we could calculate the oxidation state of carbon and this sort of thing, but that's too complicated. It's just easier to take a look and see. If I added an oxygen-carbon bond and taken away a carbon-hydrogen bond, those are the best ways to do it. So alcohols can be oxidized to carbonyl compounds. Carbonyl compounds can be reduced to alcohols. That's basically the process we're going to talk about. So I think that these reactions are the new reactions that we're going to talk about today. Let's talk about reductions first, because I think that they're the easiest. Let's talk about reductions first, because we've seen some of the reagents that are involved in reductions. Okay, so let's do some reductions. So what carbonyl compounds are we talking about? I guess that's the first thing we should talk about. We'll talk about aldehydes, ketones. So we'll talk, these two are there's going to be a sort of an invisible barrier here, which I'm going to put up here. Esters and carboxylic acids. I'll put a little dividing line between the two of them. So, and the reason why I'm doing this is because ketones and aldehydes, they behave similar, and esters and carboxylic acids behave ever so slightly. There's a nuance to them, so that's just why I'm doing this. So what we're going to see is that aldehydes can be reduced to primary alcohols. Ketones can be reduced to draw this as a tetrahedral secondary alcohols. And on the other side, both of these, when it comes to being reduced to alcohols, are going to be reduced to primary alcohols. So these are all the reduction reactions. So aldehydes, primary, ketones will be secondary, and then esters, they'll be in carboxylic acids. When they are reduced, they'll be reduced to primary alcohols. So what we actually need to do is that in each case, what we're technically doing is we're adding a hydrogen to the carbon, and we're adding a hydrogen to the oxygen here. So 2 hydrogen atoms are being added, one to the carbon, one to the oxygen. And for these reductions, the best, what we're going to see is that the hydrogen in orange, so this orange hydrogen, this is going to be, the source is going to be a hydride. So that's H negative. And the hydrogen in blue, the source is going to be H plus. So hydronium ion. So the it's actually, you can do this. Yeah. So one source is going to be H minus. The other one is going to be H plus. So this is going to be effectively a 2-step process. Because you couldn't have H minus and H plus together, they're just going to combine and make hydrogen gas, so to speak. So let's look at the two, or the reducing agents. And you will have seen these before in a couple other places. The first one is NaBH4. So sodium borohydride. And we just saw this in the last section when we were doing the oxymercuration reaction. And at the very start of Organic 1, I had a couple of structures, and I said, okay, draw the Lewis structure for these, determine its shape, if there's any formal charges, place the formal charges where they're supposed to be. And so for this one, so sodium is basically the cation, and BH4 is the anion, and technically the boron has got the formal charge of minus, but this is essentially a source of H negative. So we would do something like this. These electrons go and attack some delta plus. So the hydride is going to attack the delta plus. So this is the first one, and I believe that we're going to use this in the lab during the reduction of benzophenone, a couple other benzaldehyde, that type of thing. There's another reagent that's very similar to this, which I'll draw right beside it. Oh, what am I doing? And this guy is called, come on, move over. Lithium aluminum hydride. And some textbooks, lithium aluminum hydride, abbreviate this LAH. And if we were to draw this out, this would look identical in every way to the sodium borohydride. The only difference is that the counter ion, lithium instead of sodium, and aluminum instead of boron. But remember, aluminum is right below boron in the periodic table. And so again, this is a source of H minus. And as we did before, these electrons are going to go and attack some delta plus. Now, of the two these two reducing agents, the lithium aluminum hydride is the stronger one. So this one is more powerful. Sodium borohydride can be used in protic solvents. In fact, the common solvent for sodium borohydride to use is in methanol, which is interesting. So if you put a lithium aluminum hydride in an alcohol, it would explode. It would catch fire and all sorts of fun stuff. So for this one, you'd have to use aprotic solvents. Right, so things like THF is our most popular solvent for this. Okay. So these are our two reducing agents that we'll talk about. And they both attack delta plus. So now what we're going to do is we're going to go back and we're going to look at our carbonyl compounds, and we're going to see where delta plus happens to be. So let's talk about so if we were to draw an aldehyde or a ketone, I'll just draw an aldehyde for the sake of, if we were to say find the polar bonds in this molecule, we would say, well, we've got a polar bond between carbon and oxygen. Let's make this. So the oxygen's delta minus, the carbon's delta plus. We wanted to draw a resonance structure of this. We could say there's a pi bond between atoms of different electronegativity. So we should be able to draw a resonance structure that looks like this. And in both of these cases, we see that we've got either carbon with a formal charge of plus or a carbon with the delta plus. So the carbon of the carbonyl is the electrophilic carbon. So the way that this reduction would work is that it's, as I said before, it's a two-step process where the first thing you would do would be to mechanism. We'll use the sodium borohydride as the These electrons attack here. And then we're going to form a bond between carbon and hydrogen. We need to break a bond, and we're going to break the pi bond, and it's going to go on to the oxygen. So this is going to give us our intermediate here. So this alkoxide anion. So this is where it's going to stay until this would be step 1. And so you would stop the reaction by adding your source of H+. So step 2, you would add in some H3O+, and then this will get protonated. So oxygen's going to grab that proton, and you end up with your final product, which is the alcohol. So whenever we do these reactions, you will see a, so if we had, say, cyclohexanone, and we did this, one step would be NaBH4, step 2 would be H3O+, and then our product would be we don't draw, I'm not, because it's a skeletal structure, I'm not drawing the proton on that, on this carbon here, because it's a skeletal structure. So it'll always be like 1 step, 2 steps. And basically that's a very simple reduction of aldehydes or ketones. So in this case here, like I had a proton on this side, really just replace that with any other carbon and the mechanism's exactly the same. So the way that I've drawn this attack here in this part right here, I guess I should bring something to everybody's attention. A lot of textbooks do this where the arrows I've shown, but it gives the impression that the way that this hydride attacks. So if we think about our carbonyl, I will draw the pi bonds here. So we've got a pi bond, and remember, we're breaking the pi bond. So we've got our hydride coming in to attack. The way that I've drawn this diagram up here, where I've got this orange arrow going between the R group and the hydrogen, it might give the impression that this is attacking in a fashion, draw this in red, like this. But in fact, that's not the way it's attacking at all. It's technically attacking, that, remember, if we're breaking a pi bond, we have to, the way that it attacks, it has to attack the pi star orbital. So remember when we're doing an SN2 reaction and you had your leaving group, the sigma star orbital for here was on the opposite side of this bond, so the sigma star. So when the nucleophile attacked, it had to attack the sigma star. So because we're breaking a pi bond, we have to actually break the pi star orbital. So the pi star orbital is what it looks like would be, it's the anti-bonding orbital So when they're in phase, it's a pi bond. When they're out of phase, it's the pi star. So it has to be attacking this sort of lobe here, or this lobe here. But the key point is that it would be coming in either from the bottom or from the top. The angle isn't exactly 90 degrees. It's a little bit, it gets deflected a bit by the oxygen. But anyway, that's something for a different class. But the key point is that it's coming in perpendicular as opposed to what I've drawn in red up here, where it'd be bisecting the R and the H. But that's just the. So, right. So if we have some ketones or aldehydes, we can draw any one we want. Do this. 1, lithium aluminum hydride. 2, H3 plus. 1, sodium borohydride. 2, H3O plus. So we would end up with secondary alcohol, primary alcohol. Quick question. This product right here, this would be, what type of stereoisomers would be stereoisomers would be produced in this reaction here to form the secondary alcohol? It would be a mixture of what? Right, it would be a mixture of enantiomers. So because we've got a methyl group on one side and a propyl group on the other. So it would be a mixture of 2 enantiomers there. In the case of primary alcohols, it's just a primary alcohol. It'll just be 1 stereoisomer. Okay, good. So that's basically how the reaction works for ketones and aldehydes. Exactly the same. Now, what gets interesting is, if we go back to the top, is what happens with esters and carboxylic acids. So we'll look at that quickly. We'll do esters as the example. Later on, we'll talk about the carboxylic acids in greater detail. Reduction of esters / acids. Okay, so to reduce an ester or carboxylic acid, you need to use lithium aluminum hydride. Sodium borohydride isn't strong enough. There's the odd ester that sodium borohydride will reduce, but typically they do a very bad job of it. So for the sake of this course, when it comes to an ester, you would want to use lithium aluminum hydride, not sodium borohydride, because it's not a reliable reaction. So you can find the odd example of it where it works, but lithium aluminum hydride always works. So now the way that this reaction works is ever so slightly different. So let's look at the mechanism here. So we have our ester. I'll call it, we'll do a methyl ester, I guess. R. All right, so hydride attacks the delta plus, electrons move up. So let's draw here, delta plus. What this is going to do is this is going to give us so in this case here, I drew the H pointing towards us. It'd be a mixture of the two because it could attack from the top or the bottom. But for the sake of, I'm just drawing this like in this fashion to show that this is tetrahedral. Now, in the case of the ketones and aldehydes, this tetrahedral intermediate was stable. In this case, though, it's not. These electrons can technically come back down and boot out this methoxide. So, and this is what happens. So you boot out methoxide. And what you end up with here is an aldehyde. And this reacts very quickly with another equivalent of lithium aluminum hydride. And then this becomes our stable tetrahedral intermediate, where you've got RCO. Stable. So if these electrons are coming down, you'd be losing, you can't, this reaction, which I'm just doing this, isn't allowed because you can't lose this or R minus. Those are all very, very basic species. So this tetrahedral intermediate over here in green is stable. Whereas the tetrahedral intermediate over here, because you've got something with the OMe minus, this isn't particular, this is basic, but it's not as basic as hydrogen minus or carbon minus. So it can be booted out. And then the aldehyde reacts and you have the stable intermediate. And then the second step is exactly the same as before. So we would add H3O plus. The second step when the reaction's over. And these grab, oop, darn it. What have I done? And that would give us our final product. Which is a primary alcohol. Yeah, there's a couple of interesting things about this little reaction here. The first being that if you were to compare the reactivity of an ester versus an aldehyde, aldehydes are more reactive. Mainly, one of the reasons why aldehydes are more reactive is that esters, there is this resonance structure that is important, I guess, where you can, the oxygen can add donate its electrons to the carbonyl, and you've got a resonance structure like this, and then it of course goes back. And so you're adding electron density to that carbon, which makes it less of a delta plus. So that's one of the reasons. The other reason which makes an aldehyde particularly reactive is that the hydrogen on one side.
Dr. Hill,
yep.
Your screen's not sharing right now.
Oh, so thank you. Let's see here. Screen share. Why did the I didn't even see the little chat thing either. Okay, so does everyone see it now?
Yeah.
Yeah.
Okay, good. Sorry about that. Okay, so right, so this, what I was trying to say is that this resonance structure down here, this makes, it's one of the things which contributes to the fact that esters are slightly less reactive than aldehydes or ketones. So you need a stronger reducing agent to get this to work. That's why it's lithium aluminum hydride as opposed to sodium borohydride. If you think of, remember, aluminum's lower on the periodic table than boron. So it's going to be more electronegative, more electropositive, which will make that aluminum hydrogen or aluminum hydrogen bond more polarized towards where the delta and minus is on H. So the more, it's like a stronger source of H minus or hydride. So that's, so you really need the lithium aluminum hydride to react with esters. So yeah, so I guess the key point is that if you've got an ester, actually, let's do this. So let's say you had a compound which looked like this. If you were to do a reduction using sodium borohydride, H3O plus, only the ketone would react. So you would end up with this. If you did the reaction with lithium aluminum hydride, and we're assuming there's an excess here, then we end up with, you reduce the ketone, but you also end up reducing the ester. So you'd end up with a diol. So both, so you could say in a way that sodium borohydride is more chemoselective. So it'll reduce some functional groups and not other functional groups, whereas lithium aluminum hydride is going to reduce both aldehydes, ketones, and esters. But yeah, the mechanism is similar in many ways. It's just the hydride attacks that delta plus of the carbonyl, generate a tetrahedral intermediate. In the case of esters, it breaks down to lose the methoxide to generate an aldehyde, which gets further reduced. So that's basically how that whole thing works. So, so for our toolkit here, one of the methods to make alcohols is from aldehydes and ketones using NaBH4 or lithium hydride or esters and acids using lithium aluminum hydride. Yeah, fun stuff. Okay, so now there's a reaction which is very similar to this reduction, which you guys just finished doing in the lab last week or before the break. So in both of these cases, what we've got is we've got our carbonyl, and we're adding H- to it. Now, you could replace this H- with R- and do exactly the same thing. And so instead of making, and so we just need to figure out how to make an R-. And you guys made an R- in the lab. So what was the R- that you guys used in the lab? It was a lab where you guys used dry ice. Yes, that's right. Grignard reagent. Right. Wonderful. So we've seen a couple R- in the past. So the most common R- we've seen is, we just did one in one of the questions earlier. So we had methyl lithium, right? And so this bond is polarized in this direction. So let's draw it with all its little constituent parts here. So this is polarized in this direction. So delta plus, carbon delta minus. So technically C minus, like methyl minus. Okay, so alkyl lithiums are sources of R minus. Now the trouble is that alkyl lithiums, they're not as easy to make as Grignard reagents. So they're a source of C minus, but they're not as universally available, at least not. Yeah, they're not as universally available as. So a Grignard reagent, the fun thing about a Grignard reagent is that you take some alkyl halide. So alkyl halide. So X can be BrCl. Now, the most common Grignard reagents are probably the bromides. it all has to do with, there's a couple of things, like, they just seem to be the Goldilocks of the Grignard reagents, where, so when you're making these, you have to use an aprotic solvent. So you guys made your Grignard reagents in diethyl ether. And there's solubility issues depending upon what the counterion is. So sometimes the iodo versions aren't that soluble, or the chlorine ones take too long to make. And so, but the bromides seem to just work the best. So often those are the Grignards that are used. And so if you've got some RBr, for example, what we did was we took some magnesium metal in ether, and is basically an insertion reaction where you made this. And if we look at the periodic table, magnesium is in the second row on the left-hand side. So this bond is polarized in this direction. Magnesium plus, R minus. So basically a source of R minus. And so these are basic and nucleophilic. So you can't do a reaction in a protic solvent, or else it's just going to react with the proton. So if you try to do a Grignard reagent in, say, methanol, so let's say we tried to do this in methanol, the moment you form this, it would react with the proton of methanol. So it's always, these reactions are always done in aprotic solvents like diethyl ether or THF. But they're also really good nucleophiles. So if we've got our carbonyl, I'll make it an aldehyde in this case. And let's say you had R star MgBr. This reaction is going to be, it's completely analogous to the reduction, except for the thing which is doing the attacking is a carbonate, is a carbon, so of some flavor. So it could be a methyl, it could be a isopropyl, whatever it would be. And then you've got R, carbon, R star, H, negative. Then the second step, so this would be step 1. The second step, we want to protonate our step 2, H plus, so H3O plus. This would be, grab that, and this is going to give us our alcohol. Now, what you guys did in the lab was that you quenched yours with dry ice, right? So that creates an entirely different, that creates a carboxylic acid. I guess we could do the little mechanism of that. But the interesting thing here is that if we were to look at, I'll just do this quickly first, aldehydes, ketones, esters. put here excess. So if we do an analogous sort of reaction to, as we did at the very start, we look at these three functional groups. So this would be step one. And then the second step in each case is 1, 2 would be H3O plus. So we need the second step. 1, 2. 1, 2. What we're going to see is that aldehydes now make secondary alcohols. Ketones now make tertiary alcohols, and esters now make tertiary alcohols. So in the previous, when we're doing the reduction, aldehydes are making primary alcohols, ketones are making secondary alcohols, esters are making primary alcohols. Now it's sort of like now we're adding carbon, so aldehydes will make secondary, ketones will make tertiary, and esters will make tertiary as well. The key part about the esters is that R star is added twice. So you can go back to the reduction mechanism with lithium aluminum hydride with an ester and redo it using the Grignard reagent, and you'll see why you get 2 R stars on there. So this is really, really interesting. So the nice part about the Grignard mechanism is it's exactly the same as a reduction, except for instead of adding a hydride, you're adding R minus. So that's basically where we're going. So I guess I could have put the carboxylic acid for, we'll talk about that later on in the course though. So that's the neat thing about, and technically an addition of a Grignard reaction or reagent to a carbonyl is technically a, it's still a reduction because you're losing a carbon oxygen bond to make it's going from a double bond to a single bond, so it's technically still it's still technically being reduced. That's why organic chemists are a bit so it's technically doing, where are we? Oh my god, I missed that. Where is it? Right here. It's technically still a reduction. Instead of this H here, it's a carbon atom. But anyway, a couple of, so for what you did in the lab, oh, come on. Sorry. Carbon dioxide it's still got a delta positive here, delta minus. So it's still just coming in and attacking. Electrons move up. The only difference here is that what you've got is R carbonyl. And because this is in resonance, there's lots of electron density around that carbon. It doesn't add twice unless you really do some heat it up. And you weren't doing that. It was actually getting cold because you had the dry ice. So this stays as a stabilized anion until you add your acid. And that gave you your carboxylic acid. So that's basically how that worked. It's a neat little reaction. The trouble is that dry ice, because it's so cold, there has some water in it. And so one of the obvious side reactions is that this can go and grab part of the protons of one of the water protons, and that would give you RH. So that's not what you're looking for there. That's one of the using dry ice, because it's so cold, it sucks water, moisture out of the air. And so there's always a little bit of water in there, which could be the side reaction, which you don't want. But it's a neat reaction to make carboxylic acid. So we'll do this a bit later on in the course. But the workup for this was really easy because you could do an acid-base extraction to get your carboxylic acid. Anyway, I blabbed on way past the end of the class. The one thing I wanted to mention was that, so the top hat mark says it's out of 34. I can't change that. It just keeps on saying it, but it's really out of 27. So just keep that in mind. Whatever you got is out of 27, not 34. All right, if you have any questions, was there any questions? You can stick around and ask them, or you can ask them now. Otherwise, we'll see everybody on Thursday. Oh, there's a question. So I'll see everybody on Thursday. If you have any questions about anything, just shoot me an email. Anyway, yeah, have a have a good day. I hope you had a good reading week, and I'll see everybody soon.
Thank you.
The people which did a bonus, I did add that to question as a part to one of the questions. I just added that in, so it is added in now. Yes. Okay, what am I doing? I'm turning off that.